Right now, a message to Mars can take nearly 25 minutes to arrive. That's not a glitch. That's physics. Every command, every course correction, every emergency response travels through millions of kilometers of silence. And when the sun drifts between us, weeks of distortion, dropped packets, radio chaos. So what if we stopped fighting distance and started redesigning the link itself? Not louder signals, smarter ones, quantum ones.
You click to find out if quantum computing can actually shrink the distance to Mars. Yes, you're in the right place. Today, we'll map how qubits, photons, and quantum memories could turn delayed, noisy radio signals into secure, high-fidelity links across the solar system. But here's the twist we'll unpack. If radio fades, why can't we just switch to lasers? And what does quantum really add? Stay with me as we reveal the specific bottlenecks in deep space RF, the role of entanglement-based repeaters, and how these pieces enable near real-time navigation updates without drowning in solar interference. If light is the fastest thing we have, why does a message to Mars still feel like shouting across a canyon? The short answer is distance multiplies every weakness in our link. Even at light speed, Mars can sit so far away that a signal leaves now and doesn't show up for roughly 24 minutes one way. That delay alone turns real-time into scheduled updates. And while the clock ticks, radio waves spread out, get faint, and fight noise the whole trip. Here's the setup. Classical deep space links ride on radio frequency carriers. Energy drops with the inverse square of distance, so double the range, and the received power falls by a factor of 4. Over tens to hundreds of millions of kilometers, that compounding loss slams the signal floor. Bandwidth stays narrow to keep noise within control, and dishes grow to stadium sizes to claw back gain. You can pump more wattage and sharpen the beam, but the math of free space path loss still drags you down. Now the paradox. Bigger antennas help, but they also demand tighter pointing. A fraction of a degree off, and you spray energy into emptiness. Crank up power, and you also lift the noise riding with your electronics. Meanwhile, the universe doesn't quiet down for your call. Background radiation forms a constant bed of hiss, and our own star adds broadband chaos. The sun behaves like a loud neighbor with the TV blaring across every channel. Think of it like trying to light a friend's face across a stadium. A flashlight throws a wide cone. By the time it reaches the other side, the glow is weak and scattered. A laser pointer sends a slim shaft that actually lands where you aim, so the target gets a usable spot. That's antenna gain and beam spread in plain terms. Radio acts more like the flashlight unless you carry a massive, well-aimed dish. Even then, tiny jitter translates into big losses. Real missions live with these limits every day. Rovers on Mars don't chat directly with Earth most of the time. They bounce data to orbiters that pass overhead, which then forward packets to the deep space network. When they do aim straight home, the bit rates drop to a trickle. DSN time is rationed, with spacecraft queuing for windows that fit both geometry and workload. It's a crowded highway with limited toll booths. Then comes solar conjunction. When the sun lines up between Earth and Mars, weeks of degraded or halted comms follow. The hot plasma near the sun bends and jitters radio waves, mangling phase and polarization. Commands risk corruption, and telemetry turns unreliable. Operators plan around it like seasonal weather, blackout weeks where patience, not power, carries the day. You've seen the consequences. A probe far beyond Mars can spend hours returning a single image. Ambitious missions budget around DSN schedules like airline slots. Concepts that dream of gram-scale craft racing outward run into a hard stop when the downlink can't keep up with the flight plan. Classical telemetry sets the ceiling, not the imagination of the payload. So we look to optical links. Lasers reduce beam spread dramatically, translating to higher received power and fatter data pipes. Demo missions have proven clean, high-rate optical downlinks, and new systems push those numbers higher. But the upgrade has its own checklist. Pointing becomes surgical. Dust, clouds, and atmospheric turbulence cut into ground reception. Near the sun, stray light and plasma still bite, shaving margin from your link budget right when you need it most. By now, you can see why the delay exists, how distance erases radio power, and how the sun can impose multi-week quiet hours. Lasers lift the bitrate, but not the lightspeed wall, and they don't erase solar seasonality. So here's the next step. If photons can't outrun physics, what do qubits and entanglement bring that classical beams never will, especially when the clock and the sun both say no? Lasers lift bitrate, but they don't erase delay or solar blackouts. So how can quantum make Mars feel closer without pretending to outrun light? It changes what we send and how we coordinate. Instead of pushing louder signals, we pre-stage correlations that let the link act smarter under stress. The trick is entanglement. You share paired quantum states ahead of time, then use them to move information with fewer retries, tighter security, and timing that holds its shape when the sun starts to roar. Here's the ground rule. Quantum doesn't grant faster than light messaging. What it adds is a new resource, correlation stronger than anything classical can offer. With those, you run quantum key distribution to generate fresh, provably secure keys even while the background howls. You also gain quantum teleportation, where the state of a qubit transfers from one location to another. That transfer still needs a classical ping to finish the job, so the speed limit survives. But the payload, the fragile state, doesn't ride the lossy channel directly. People often hear entanglement and assume instant chat. That's the trap. No message crosses space without a classical side channel carrying the final bits that complete the operation. What you win is reliability and integrity. Even if the classical line stutters, the sensitive quantum piece can be reconstructed perfectly once the delayed classical bits arrive, which slashes the need to resend complex data and keeps control loops from drifting. Now the architecture. A deep space quantum backbone strings together quantum repeaters, satellite nodes, and quantum memories. Repeaters don't amplify unknown quantum states. They create and swap entanglement between segments. Satellite nodes distribute entangled pairs across long free space lengths. Quantum memories store those pairs long enough to stitch segments into a continuous corridor. Through entanglement swapping, the endpoints end up entangled even though they never shared a direct link. Why this matters in space comes down to scaling. Over interplanetary distances, straightforward transmission of entangled photons fades to almost nothing. Loss rises exponentially with distance, so a direct shot rarely survives. With repeaters and memories, you build the connection step by step. Each hop is short enough to be feasible, and the overall resource cost grows polynomially instead of collapsing into zero yield at scale. That difference is the line between a lab demo and a workable solar system network. Think of a chain of synchronized safes waiting along the route. Each safe holds a perfect lock. When two adjacent safes agree, they swap locks in a coordinated move, and now the first and the last safe share a lock that matches exactly. Later, when you need to send a precious key, you don't throw it across the void. You use the shared lock to reconstruct it flawlessly at the far end. The key arrives as clean as it started, even if the hallway outside is crowded and loud. Lab and on-orbit work point the way. Satellites have already shown long-distance entanglement distribution across continental scales. Teams store quantum states in rare earth-doped crystals that hold coherence long enough to bridge scheduling gaps.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.